just to informing you that we are going to record this presentation, and later on we put this one in the IS channel of the YouTube channel of the IS WA chapter, so you can later on see the recorded file as well. So just let me to quickly introduce a speaker today. Dr. Yuanchang Liu received the bachelor degree in control engineering from the Dalian University of Technology in 2010, master degree in power system engineering, and Ph.D. degree in marine control engineering from University College London in 2011 and 2016 respectively, where he is currently a lecturer with Department of Mechanical Engineering. Before joining the department, he was a research fellow in robotic vision and autonomous vehicle of the Surrey Space Centre, University of Surrey. His research focuses on automation and autonomy, with a special interest in the exploration of technologies for sensing and perception, guidance and control of intelligent and autonomous vehicles. He is currently supervising 4 PhD students working on the project of autonomous navigation for unmanned marine vehicles. So again, this is my great honor to, ask the, Yuanchang to start the presentation, and the floor is yours, Yuan. If you are ready, please start your talk. Thank you very much.
Thank you. Thank you very much, Amber. I will just share my screen now, and let me know if you have any problem of seeing it. I hope all of you can see my screen now.
Yes, we can see. That's perfect.
Super. Okay. Thank you very much, and welcome to this talk, everyone. And it's my honor to give this presentation today to introduce you the current technologies in marine robotics. So today's talk will be mainly focusing on the autonomy and the automation in marine robotics. I'm going to cover the main technologies have been developed, as well as I will talk about some of my thoughts on the future development. And my name is Dr. Yuanchang Liu, and today is it's my great honor here to be here to give this presentation. And I'm currently the lecturer in the Department of Mechanical Engineering at UCL, and also I'm one of the members of UCL Robotics Research Centre. And today I'm going to give my presentation mainly from 4 different aspects. I will firstly give a brief introduction to UCL Mechanical Engineering, as well as my research team. And then I will dig into my research activities in various directions. And then I will give a brief summary about this presentation to point out some future directions. So first of all, a very brief introduction to UCL. UCL has a very long history, and founded in early 19th century. It's the 3rd largest university in the UK, and we are the largest by the number of the postgraduate enrollment. We currently have 11 constituting faculties, which covered over 100 departments, institutes, and research centers. And UCL has a very broad research directions, almost covering all the different research activities that you can think about. And because of this strong research power, UCL has a very high ranking in the world universities ranking tables. For example, in this year we are the 10th at QS World University rankings, and we are very strong in doing the research, which can be revealed by the number of Nobel Prize winners, as well as the field's medals in mathematics. And our latest staff who won the Nobel Prize was in 2014, who is the Professor John O'Keefe. And then about the UCL Mechanical Engineering, where I come from, we are the one of the first departments in the UK which provides the education in mechanical engineering, and due to we have a very long history of over 170 years. We belong to the Faculty of Engineering Sciences, and we have a large number of academic staff, including 19 full professors who provide the teaching activities to over 600 students. We're very strong in research power, of course, in the latest research excellence framework, which is one of the UK's evaluation scheme for universities research. 90% of our research activities in the department are evaluated as world-leading or international excellent. And so, and we have very broad research interest in various aspects. For example, we divide our research group into 4 different areas, including the energy, biomechanical, materials, and marine. And one of the research activities that has been quite proud to introduce you is that we normally have our research outcomes published in very high impact journals such as Nature's, Science, and etc. And the Marine Research Group is where I come from, and currently I'm leading 2 research associates and research assistants in my group, and supported by 5 Ph.D. students. And also in my group we have a very large number of master students as well each year to help with to conduct some research activities. And my research group is mainly funded by various research councils, including the regional, for example, the European councils, as well as the national research councils, including UKRI, which is the UK Research Innovation, and the Lloyd's Register Foundation and the Royal Society. And we try to do our research via various collaborations, both internationally and nationally. So, for example, my research group have very good relationship with the university within the UK, such as University of Plymouth and Cardiff University, and of course we have a very close relationship with the university from the States. For example, Stevens Institute of Technology. We have jointly published some papers and organized some workshops together as well. And of course, apart from academic partners, we're working very closely with the industries, especially in the marine aspects. We're working with Kinetic, which is one of the biggest, largest marine company in the UK, as well as BMT. And if we start talking about the specific research activities in my research group, the philosophy of my research is actually it can be perfectly shown from this picture here, where I normally we conduct our research via theoretical designs, which will be used to innovate the robotic platforms, which can ultimately used to benefit a lot of practical applications. In this diagram here, we were trying to develop the autonomous navigation systems for different robotic platforms, and we're focusing on three different aspects, including the sensing and perception, and then the planning and decision making, and finally we have the automatic control functions to be developed. And using this framework, we can apply it into different robotics vehicles. For example, if we can use them for the UAVs, with application potentially to be the precision agriculture. And of course, we can use them for the space rovers to enable this space exploration. And finally, as one of my main research interests, we use this framework for the marine vehicles for the ocean discoveries. And today, I will be mainly focus. I will focus this talk mainly on the ocean activities. And my research mainly focuses on the surface vessels, or unmanned surface vessels, short for USVs. Is one of the new technologies currently has been intensively researched or developed by both academic staffs and also industry companies. It's like the self-driving cars. The USVs can operate on the surface water without a crew member. And here are two examples I would like to show you. One is the USV developed by L3 ASV, which is a company based in the UK, and is one of the largest USV manufacturer and in the world. And in this picture here is the USV called the Springer USV, produced by University of Plymouth, and it's the first educational platform of USV developed in the UK. And in terms of the USVs and their applications, we normally can categorize the application into two different aspects. One is, of course, the military applications, which includes the coastal patrol, and we can use the USVs as the target boats for training. And of course, we can use the USVs together with some underwater vehicles for mine swiping operations. In these two pictures here is a perfect example of showing you that one of the USV developed in the UK for the patrol missions, which is currently which is being tested on Thames River in London. And this picture here is a new USV platform co-developed by Royal Navy and the L3SV. This is one of the highest, one of the USVs has very high speed, which can travel at the speed up to, I think, up to 50 knots, which is a very powerful unmanned vessels. And of course, apart from the military applications, we have the civilian applications for USVs, including the ocean environment monitoring, ocean discovery, and of course the climate monitoring and seafloor mapping missions. We can deploy the USVs together with other types of the vehicles, including underwater vehicles, and of course the UAVs and some other types of the vehicles together. This picture here gives an example of how the collaborative operation between the USVs and underwater vehicles to perform a seabed mapping missions. And in this slide here, I would like to particularly introduce you one of the flagship project actually undertaking in the UK at the moment. It's called the Mayflower autonomous ship. It's one of the ship has been designed in collaboration between the ProMair and the IBM to showcase how a autonomous vessel or USV can conduct a cross-Atlantic mission from the UK to the US. It's a 3-week voyage, completely powered by AI, and the voyage starts from the Plymouth in the UK and navigate through Isles of Sicily and over to the destination in Plymouth in the US. And during the mission, the ship can conduct the missions such as sample the water for pollutants and also study the marine life in the oceans. So here is a video I would like to show you to introduce you this a little bit more detail about this project. Hopefully you can see this video.
The ocean floor is littered with our engineering failures and mistakes. You need to respect the power of what happens out there.
There's still things to be discovered. If we have a zero risk philosophy, we are doomed.
When we first conceived of this idea, I wasn't sure it was going to be possible. We were talking about an intelligent vehicle out in the middle of the Atlantic Ocean.
We built a ship, put autonomy into it, and now we're learning what that means.
So you just maintain your course and speed.
The pressure's certainly building as we're getting closer to the launch. There's a lot that we need to deliver.
Right.
Something going wrong.
What keeps me up at night is we break down somewhere in the middle of the Atlantic, and it's something so trivial.
Working on a boat like this, you kind of have to figure stuff out on your own.
To get some drama.
No, we need to find out what happened, but it wasn't responding. So we'd lost comms.
I just want to finish shaking her out and start across.
The crossing?
The crossing.
So when you say the crossing?
Atlantic.
That little thing?
Yeah.
Yeah, good luck.
When it pulls out of Plymouth, and I know it's not coming back for 6 months, when I see the rear end of it and the stern of it going around Ream Head, headed off west, that's going to be exciting.
IBM really likes projects that are really pushing the envelope to do really exciting and novel things.
What if we had hundreds of these vessels? This is going to transform ocean science.
Trying and failing doesn't bother me. It's if we don't do everything we can do to ensure success.
Okay, so that's an exciting journey conducted by the Mayflower autonomous ships. And of course, from the video, you can see how challenging the mission is because the transatlantic, Atlantic mission, it requires a very high level of autonomy. Of course, the energy consumption should be optimized, and also we have to encounter various uncertainties during the journey to achieve the mission. So, in order to make a full autonomy for the for ships, we need to sort of develop a autonomous navigation system. And in this slide here shows you a general structure of how we can achieve the autonomy. We can see that it includes 3 different sections. The first section will be the sensors, which will help the USVs to understand and perceive the environment, and then the perceived information will be passed on to the central planning and the decision making module, which can generate which can plan the trajectories, generate the waypoints to guide the USV to travel, and finally, by receiving the waypoints for the navigation system, the USVs can use the autopilot to follow or track the waypoints and consequently finish the mission. So generally, we can group this research into 2 directions. One is the sense and the perception, which will be used to collect the navigational data and as well as the environmental information. And the second thing is the planning and control. It involves the missions such as the task allocation, motion planning, and control. And by following this framework here, where my group normally developed the technologies on sensing and planning part. So in terms of the sensing and perception for the USVs, the first issue we need to address is that how we can let the USVs understand where it is, which in other words is how we can provide a good localization for USVs. Normally, we can use the sensors such as GPS, RMU, and etc. However, all these sensors or the equipment suffer from the sensors limitations or suffer from the influences from the environment, such as winds and currents, which will ultimately affect the accuracy of the sensors. And normally we use the common filtering, such as EKF or UKF, to improve the sensing accuracy. However, we found out that one of the main requirements for the common filtering technology is that we need to have a very good estimation of the a priori knowledge of the system noises, which is not normally true for USVs in practical applications, because the environment will ultimately affect the sensing ratings, or which consequently affect the system's noises. So, in order to address this issue, we developed a new algorithm called the adaptive UKF, which includes the fuzzy logic module fuzzy logic module into the UKF architecture to improve the sensing ratings and the accuracy. So here are some results. Firstly, we test our algorithm in a case where we have a very good estimation of the sensors noises. And as we can see from the results here, the green line is the UKF readings, whereas the red line is the AUKF or adaptive UKF readings. You can see that the red line is always closer to the ground truth in comparison to the green line, which means that our new algorithm is much better than the conventional common filtering. And then we test our algorithm in a more difficult scenario, where we have a very bad estimation of the sensor's noises, and the results come back unsurprisingly that the new algorithm, which is in the red line, can provide a much better estimation in terms of the location as well as the headings of the USV compared with the UKF. And then we test the algorithm in a practical trials. We let the USV to start from here and to follow several buoys on a lake. And during the navigation, we test the algorithm's capacity of localization, which means that whether it can provide a accurate position information as well as the heading angles for the USVs. And unsurprisingly, in both cases, the adaptive uncentered common filter, or AUKF, which is in the red line, is able to provide a better performance compared with the UKF. So that's the first research that we have undertaken to provide a good estimation or good localization information for the USVs. And once the USVs understand where it is and which direction it is navigating, the second question will be how it can detect the other ships, because ultimately when the USV is traveling on for example, on the sea, it will encounter with other ships for sure, and it has to avoid these ships to ensure the safety. And one of the sensors that the ships has been using to detect other ships is to use the AIS information. The AIS is called the Automatic Identification Systems, which has been widely used in maritime navigation. Actually, the human pilot or operator normally use the AIS to let them understand the navigation situation and consequently make the right decision for the collision avoidance. And if we want to use equip the AIs with the unmanned vessels, one of the biggest questions we have envisaged is that how we can let the USVs understand the information provided AIs, because the AIs, unlike other types of the sensors, for example, the camera will give you a vivid picture information, whereas the radar can directly give you the information about the distance and the angles. The AIS actually comes with the format of text, and any algorithm is not able to process information efficiently without any if there's no pre-processing procedure happens. So one of the one of the strategies that we've come up with is actually to visualize the AIS information, to convert the textual information into pictures, and then we can use the deep neural networks to train the networks and consequently understand the information behind the AIS. And here is the results that we have used. We have tried to use the AIS information to understand the ship movements, and we can see from these results here that by using the deep neural networks, we can have a very high accuracy in detecting, in understanding whether the other ships is moving or is static. And once we can have a clear picture about whether the other ship is moving or not, then the next question is how we can assess the encounter situation and understand whether further collisions will be happening. And again, we want to purely rely on the AIS information to achieve this. And one of the strategy or approach that we have used is that we add more information into the AIS information, such as we add the collision assessment information, such as the DCPA, which is the distance to the closest point of approach, and TCPA into the AIS, and then we use the deep neural networks to take in this information and generate the proper encounter situation assessment. And from these results here, we can see that by taking the information from the AIs and by assessing the encounter situations, the deep neural networks can provide a very good estimation about whether, first of all, whether the ships is going to have the risk, and if there is a risk, what kind of encounter situation will be happening? Is it crossing, or is it overtaking, or is it head-on situation? And based on this encounter situation assessment, the USV can then generate the proper collision avoidance strategy to ensure the safety. And a next big research area that my group is currently working on is to use the computer vision to detect obstacles on the water surface. And the reason why we want to use the computer vision is that compared with other sensors such as LiDAR or radar, the cameras can provide a very rich texture information and at a relatively low cost. And the computer vision is actually quite mature in other application areas, such as the self-driving cars and mobile robots. And one of the and normally they use the semantic segmentation for the obstacle detection in these applications. And if we want to transfer this technologies in other domain into the marine, there are two things we need to specifically address. One is the weather, because different weather conditions, especially on the water surface, will largely compromise the detection performances. For example, if we can see from this picture here, in this scenario where we have a very hazy weather on the water surface, then there's a very bad waterline detection performance, which means that the algorithm cannot perfectly distinguish where the sky is, where the water is, and that will have very negative impact on the navigation. The other environment conditions that will influence the algorithm performance is actually the sunlight reflection on the water surface. Again, from this picture here, we can see that during the very strong sunlight reflections, then again the water skyline separation cannot be reliably or robustly detected. So in order to address this problem, some people are using the model-based algorithm for this purpose, whereas in most recent years, due to the popularity of the deep neural networks, some people are using have developed different types of the artificial neural networks for this purpose. However, there's always a trade-off between the efficiency, which can be provided by the model-based algorithms, and the accuracy. And in this, and one of the work that we have tried to do is actually to compromise this difference between the efficiency and the accuracy. Therefore, we continue to use the deep neural networks architecture, but we use the mobile net as the backbone in the deep neural networks to actually achieve a very high efficient detection result by not compromising the accuracy. So here is the result I would like to show you here. That first of all, by using the new deep neural network structure, we can achieve a real-time performance where the algorithm is working at about 25 FPS, and then we can see that the algorithm is quite reliable in various conditions, including the strong sunlight and unstable water surface, etc. And in various conditions, a very high accuracy in obstacle detection can be achieved. So here's all the work I would like to introduce you about the sensing and perception. And the next thing that we are interested in is actually the motion planning for the USVs. The motion planning in general is to plan the trajectory from the starting point to the end point while avoiding obstacles. Of course, there are a lot of different types of the algorithms that you can use, and one of the main algorithms is called artificial potential fields, which means that we assign a relatively high potential to the obstacles and relatively low potential to the goal point, and consequently, the generated trajectory can travel from the start point to the end point while avoiding the obstacles en route. And the reason why the artificial potential field is very interesting is that it can ensure the path to be smooth and to be reliable, and most importantly, it can ensure the completeness of the trajectory, which means that as long as there's a trajectory existing, then the algorithm can always find it. So using the artificial potential field concept, we have tried to use this in different scenarios. In the first two simulations here, is that we use the algorithm to address the USVs to plan the trajectory and under different ocean currents conditions. We can, as you can see, that the trajectory can be very adaptive according to the directions of the ocean currents to effectively save the energy consumptions. Another work that we've worked on is that we try to address the multi-USVs coordination and the collaboration problems to avoid both the static obstacles and the dynamic obstacles. And of course, from the results here, we can see that these issues can be well addressed. And probably you can see from the previous slides that all the results that I've presented to you in motion planning has been primarily in the MATLAB. However, we think that in order to achieve a high autonomy or automation for the USVs, we need to sort of conduct research in high-fidelity simulations as much as possible, which sometimes MATLAB cannot provide you. And recently, we've been switching our focus from the MATLAB into ROS, which is the robotic operating systems. ROS has been largely used for other types of the robots, including mobile robots, including the UAVs, etc., but has not received equivalent attention for USVs. So we want to encourage this work in ROS for the USVs as much as possible, and therefore we use the we developed a real USV engine in the ROS, and consequently you can see that we can achieve a relatively high a relatively real-time performance in ROS by simulating the ocean environments. And then we have developed a autonomous navigation architecture in ROS to achieve the USV autonomy. As you can see here, we have the motion planner, and then the motion planner will pass on the trajectory information to the navigational refine system, which can then generate the desired velocity and the rudder angle for the autopilot. And the autopilot will consequently generate the control commands to the USVs and consequently guide the USV to track the waypoints. And in terms of the autopilot development, of course, we can use different types of controllers, and currently we're developing the PID controllers to achieve this. And here's a simulation result in ROS that we've tried to test the algorithm's capacity of how a USV is able to navigate in a wind farm, offshore wind farm scenario to conduct the investigation missions. So as we can see, we can perfectly simulate a offshore wind farm scenario, whereas the trajectory has been smoothly generated, whereas the USV here can perfectly follow the trajectory by avoiding the wind farm, the turbines, and we can provide a real-time speed and rudder angle for the USVs in gazebo or in ROS. And then Moving away from the simulations, we have also tested our algorithms on real boat, which is the Springer USVs that I introduced in the very beginning. This is joint test between UCL and the University of Plymouth, and the test has been undertaken mainly to validate the data fusion algorithms and the motion planning algorithms. And here is the video that has been recorded during the test. We let the USV starting from one point and continue to follow the other waypoints along the route. And we have put a virtual obstacle on the lake to specifically test the collision avoidance capability of the USVs. So we can see that the USV is able to follow the waypoints quite robustly. However, there is a sort of deviation between the actual trajectory taken by the USV, which is shown in the blue line, and the ideal trajectory, which is the dashed line here. And the reason why this is a deviation is that, first of all, the motion of the USV is largely constrained by its dynamics, which means that when the USV is requested to make a turning, it cannot exactly the turning in a very flexible way. And secondly, the deviation is caused by the environment conditions. For example, during the day, as you can see from the video here, we have very strong wind, we have very relatively high waves on the lake. Therefore, this environment influences push the USV away from the desired trajectory, and affect the trajectory tracking performances. And that's the reason why we would like to conduct. We want to generate the trajectory that has been compliant with the environment conditions as much as possible. Finally, the research that I would like to introduce to you is that apart from the conventional motion planning algorithm development, we also want to try how we can use the machine learning algorithms to benefit the USVs. One of the things that we've tried is to use the reinforcement learning to train the USVs to generate the navigation actions. And actually, we have followed the standard framework of reinforcement learning, but expanded into the USV applications by developing a new system structure of how we can better represent the USV's dynamics, the USVs, for example, if we have multiple USVs, how we can represent the coordination of the USVs into the reinforcement learning. And we follow for example, in this work here, we use the typical deep queue networks to train a USV formation to let them avoid the obstacles and generate the navigational actions. And as we can see from this result here, by using the reinforcement learning, the USV formation can generate a quite smart decisions when it encounter an island on the route. And also by using the reinforcement learning, the USV formation can pass through a very narrow channel while largely keep the formation shape as much as possible. And of course, we have used another type of the reinforcement learning called the DDPG to train the multi-USVs formation control. In other words, we want to train the USVs to learn how they can form the formation shape and retain the formation shape during the navigation. Right. that's pretty much all the research activities that I would like to introduce you today. And to summarize, we've conducted a broad range of research activities in autonomy and automation for marine robotics, covering the research in sensing and perception, and of course the motion planning and control. And of course, we think that the developed technology cannot only be used for the marine robotics, but also for other types of the robotics in our daily life. For example, the transportation, agriculture, and of course in other other domains like the communication and the household daily life. And as I mentioned before, we've intensively used the machine learning algorithms in robotics, but there are some other questions we would like to answer in the future if we want to the machine learning can benefit the robotics in a better way. First, we need to ensure that the AI is trustworthy. In other words, we need to make sure that we can understand how the AI can generate the outputs. Yeah, how the AI and how the AI can understand the internal mechanism of the neural networks, and then we want to achieve a generalization of the learning, because mostly the AI has been developed specifically for one purposes, and how we can sort of generalize the capacity of the AI is a big question in the future. And of course, the AI relies on very large number of data for training. How we can improve the AI technologies by using a small number of training data, but provides a very high accurate results. And of course, we have some thoughts on the robotics as well, because if we want to further push forward the boundary of the research in robotics, there are three questions we want to answer. The first one is that how we can address the sensing, planning, and control problems in a more comprehensive way, because currently the three modules are being investigated kind of like separately. Of course, we have the end-to-end technologies being developed, which combine the sensing and control in a comprehensive way. But the performance is not as good as we expected. And of course, it relies on more research into possibly better AI algorithms, of course, and also how we can represent the AI algorithms in a more rigorous way, potentially using more rigorous mathematics to represent the system's dynamics. Okay, that's all for my today's presentation, and I'm happy to take any questions.
Thank you very much for your very interesting presentation, very contentful, including the recent advancement and technology of the unmanned surface vehicle. So it's time for the audience to ask the questions from Dr. Yuanchang. So please feel free to ask your questions. So I may start with the first question, Yuan. So you mentioned today very, substantial questions in your, final slide, in your conclusion slide. And that was one of my questions. So how far we are to have a sort of comprehensive, integrated, sensing, navigation, planning, control for such a practical and complex USV systems. can we rely, for example, on the AI for such a safety critical systems? Because you know that is always a debate between two groups. That's one on the pros and cons of the AIs, especially for such a critical system. I appreciate if you briefly answer to this question.
Okay, yeah, thank you. I think that's a very good question. And as you mentioned, how the AI can actually benefit the robotics has been largely debated by both academic staff and the colleagues from industry. Of course, AI can provide is very intriguing in providing a very high performance of in various domains. But as mentioned, one of the biggest problem with AI is that we cannot fully understand the internal mechanism. For example, if they are using neural networks, we cannot fully understand the internal mechanism of how their networks, what is going on within the networks, and consequently how the results have been generated. And if we apply that onto the robotics, for example, self-driving cars, the question will be how reliable the control has been generated, and how safe and how trustworthy these things can be these things are. So the question is, we need to put I think to answer your question about the future development, I think there are two things we need to be focusing on. First of all, of course, we have to continue to develop AI, especially to better understand how the AI is actually operating. And the second thing that we need to be very focusing on is actually apart from the engineering side, or the development side, I think there's big work going within the regulatory side as well. Because as long as the technologies have been developed, the next question is how this new technology can be accepted by the society, and how these new technologies can be better regulated. Therefore, there are a lot of policies, for example, or regulations needs to be consolidated to enable a better application or implementation of the AI.
Thank you very much for your answer. Yeah, fair enough. Yeah, I know the challenges and you're completely right. So any more question? So before leaving, feel free to ask your questions.
Hello, thank you very much. My name is Farad, and I'm generally an electrical power engineer, but I really loved and amazed by those discussions which you had about wind turbines and wind farms, because this is an aspect that when it comes from electrical engineering perspective, we really don't care that much. We consider mainly about the voltage, current, power, control of those things. But there is that significant mechanical part behind that, which, like the technologies which you were showing, is a very amazing way to try to observe, monitor, troubleshoot any of those aspects. So yeah, not a question, but I just want to say that it's a very interesting area that I had never thought interestingly before, that those wind turbines are also a key focus of studies from mechanical parts, and especially those type of automated systems that and robotics that are used for evaluating those things. So thank you very much. That was very eye-opening for me. Thanks.
Thank you very much. Thank you for comments. I think one of the reasons that we want to develop the USVs for the offshore wind farm operation is that there's a large initiative going within the UK to sort of because of the decarbonation of the decarbonation mission globally. Yeah, we want to use the offshore wind as much as possible to replace the fossil fuels. So there are lots of wind farms, offshore wind farms developed in the UK, And one of the biggest issues with the increase of the number of the farms is to actually the investigation and the maintenance of these wind farms. We can also, of course, rely on the humans to do this, but I think in a better way is that we can deploy the robotic systems to achieve that, and therefore that inspires us to use whether USVs can play a key role in this task. And yeah, thank you.
Yeah, thank you. Thanks very much. I definitely agree with that. Thank you.
Thank you very much, both. So any further question? Seems there is no more questions. So I thank you again. So for your very interesting presentation, we enjoyed a lot, and hope to see you next time again.
Thank you very much. Thank you all.
Thank you everybody for attending this webinar, and have a good evening.
Thank you. Bye.
That's the end of session. Thank you.